super formal.
So my name is Neha. I work on ML serving at Pinterest, like for access models. So um, coincidentally, today's topic coincides with VLLM, which is one of the serving frameworks out there for serving large language models in production. Um, the VLLM framework is based on top of this paper, which is efficient memory management. Um, for KB cache and which is specifically called like paged attention. And we'll go through this paper for the rest of the talk. Yeah. Um, so the way I thought about going through VLLM was like two parts. One was like going through the original contribution they have, which is basically page attention. And on top of that, this paper was published in like 2023, and it's like almost 2026 now. So they do have a lot of other improvements on top of their original VLLM implementation. So we try and go through, the goal is to go through like as much as we can of page attention today. And then in the next week's talk, we can go through the other stuff related to batching and scheduling.
That's good.
So we can go through the abstract first, and then we can jump over the pieces which many of you already know here, and we can talk about the relevant stuff. So high throughput serving of large language models requires batching sufficiently many requests at a time. This is not new. It's true for training. It's true for inference. GPUs are designed for handling large batches. So if you want to use your GPU efficiently and get return on investment for the GPU cost, it's like you want to batch as many requests as together, basically for training as well as inference. But this is particularly a challenge for inference for large language model because something like we call the key value cache memory for each request is huge and grows and shrinks dynamically. Um, the paper talks like they give like a lot of diagrams which are pretty helpful. Like this is like NVIDIA A100 40 GB memory. You can see if you look at the memory profile, like parameters, this model they've loaded as like a 13 billion parameter model. So 13 billion parameter model takes about like 65% of memory, 26 gigabytes. But if you look at the KV cache, the remaining 30%, like out of the 30% of the memory is used by the KV cache. And the others is just activations and other stuff. So a large portion of the memory is used by KV cache, and this is how LLMs differ from traditional models like convolutional neural networks or XS, where if you look at a memory profile of a convolutional neural network, the memory would just be occupied by the model parameters and the activations and maybe the input image. It won't have this big component of a KV cache, which also changes dynamically. Like if you look at input image in a convolutional neural network, it's a fixed size and a model would only accept that size. There are very few models which actually can do dynamic sizing. So this dynamic changing of memory per request is what is the most challenging part here. Um, the reason being, it's not just about how much memory you use, but it's also about how you allocate and use it so that you avoid like basically you avoid fragmentation and duplication and you're not wasting memory. So based on this problem specific to LLMs, this paper proposes page attention, which is an attention algorithm inspired by the classical virtual memory and paging techniques in operating systems. So this is very similar to the problem you have in operating systems where um, not all processes occupy the same amount of memory in a RAM. So how would you account for like a Word document which is open with 100 pages requiring a lot of memory versus like a calculator which doesn't require a lot of memory. You possibly won't allocate like same memory size to each of them. And kind of like in the operating system space, people came up with the concept of virtual memory and paging techniques and a page table and that kind of stuff to have this dynamic allocation per process where you avoid wasting memory. So they kind of apply the same technique to the GPU memory. And they also develop like VLLM and LLM serving system. And they show that it wastes zero memory, and they also improve it further where you can share memory across different requests. They do evaluation. So if you look at the graph here, yeah. So one thing that was interesting here is they're not trying to improve the latency of the model. So they're not trying to improve like um, they're not trying to improve how fast you get a response, but they're trying to improve like how many requests you can do in parallel so that you need less number of GPUs to serve it. So they're trying to improve throughput. So if you look at the orange curve in the graph here, um, for existing systems, as your batch size increases or the number of requests per second increases, the memory increase is kind of like more than linear. What they do is basically they propose this page attention technique where the memory increases sublinear or maybe linear. So for like a 40 gigabyte memory space, you can now serve around 900 requests per second, whereas in a traditional existing system, you could only serve like 300 requests per second. Yeah, I'll pause here for a moment.
Neha, I had a question. I don't recall. In the case of like an operating system and virtual memory in an operating system, the verb to page means to move between disk and CPU system memory. In the case
Right.
of VLLM, am I recalling, is it between HBM and whatever the next tier is of memory up?
Yes, but they call it different. So the concept exists in VLLM or like inference, LLM inference, but it's called KV cache offloading. It is not called page. Like I haven't heard people use the term to page.
Okay.
The idea is that when your GPU doesn't have enough memory to hold the entire KV cache, it would offload some of the KV cache to CPU. Um,
Oh, okay. So it's
yeah.
between CPU memory and GPU memory, HBM on
Yes.
the GPU. Okay.
Yeah. Yeah.
Okay.
Yeah.
Great. Thank you.
Yeah. So I'll skip most of the introduction. But basically, they go over the difference between like an autoregressive transformer with a KV cache versus a traditional model. The autoregressiveness creates a memory bound. They also give context on like if you look at GPU evolution up to H200 maybe, it was all about increasing the number of flops per second. So the GPU computation capability increased much faster than the memory. I'm not sure about Blackwell. I didn't get a chance to look at it, but with LLMs, this is the first time that you start becoming memory bound. Otherwise, GPUs have always been compute bound, and that's like the unique nature of autoregressive workloads. Um, they Yeah, so this is like let me go through this diagram because they keep talking about these models throughout the paper. I don't know what exactly is Orca. I looked it up. It's an inference system from Friendly AI, built by some university in Korea. But it is not open source. It's a closed system, so I'm not sure how it's implemented. But these guys implemented a dummy, not dummy exactly, but like an equivalent version of Orca, and they compare VLLM against it to show how memory efficient it is. So the y-axis is like KV cache usage, and the x-axis is basically all the systems. Um, they divide the memory usage into four categories. So the token states is basically the pre-fill tokens. So when you look at the process, the when you give like a prompt to an LLM, it takes in the entire prompt in one go and it processes it to produce intermediate KV cache or intermediate representation, and that they basically call it is pre-fill token. And then during the decode phase, you go and generate one token at a time. And that they call it as like the autoregressive or the decode phase. So the green one is the memory which is taken by the pre-fill phase. The yellow one is the memory which will be taken later by the decode phase. So as you start decoding, you'll decode, but you don't know how much memory you need. Like how long will you keep on generating tokens until you reach end of state token? So you need to allocate memory per request per KV cache. And this is the extra memory they allocate. So the red is, they call it internal fragmentation, but it's basically they allocated certain amount of memory per request, saying this is the amount of KV cache I need, but the other regressive phase ended earlier, so you had like extra memory left, but you'd allocated it, but you didn't use it. So this is the wastage. And then the external fragmentation is um, basically you don't um, when you allocate memory per request per KV cache, you don't allocate it contiguously, and as requests come and go, you are removing it. You're deallocating and allocating again. So you might have spaces of memory in between which are not big enough to put in a new request, kind of. So this is like the external one. Um, so the green, yellow, and red and gray mean that. Now this is a part where max means, say, suppose you say your LLM supports a maximum sequence length of 2048 tokens, then for every request, you are basically allocating 2048 token memory space. For power of two, since they knew what data set they're going to do inference on, they said, okay, the actual length of the output is this, so I'm going to allocate two times the memory. So you see, they went from max to like two times the output length memory, and you see the internal fragmentation reduces because you have less wasted memory now, but the external one increases because you have memory of varying lengths. So here the memory allocation was constant, so it led to, so let's say 2048 into X number of bytes per request. Here it would change per request, so you have like varying block sizes in memory which you've allocated, and then when these requests finish and new ones come in, they might not fit in it, so you go somewhere else and do it, and so you have more external fragmentation. The Oracle one, they said we just allocate as much as it needs, so there is no internal fragmentation. Um, but there is subsequent external fragmentation, and this is VLLM with page attention. I wasn't sure how they figured out what the actual length is going to be, but the graph kind of makes sense, and the internal and external fragmentation part of it makes sense. Yeah. Yeah, they use these terms as reference throughout the paper to indicate where the memory wastage comes from. Um, yeah. So they also, we don't need to go through this entire paragraph, but maybe just to, the TLDR, I think, was um, in traditional inference systems, since your input size is same, for each request, and your parameter size remains the same, your activation remains the same, your output remains the same. You can pretty much pre-allocate memory and do the entire request again and again, and it's fixed memory. It doesn't change with time. And they do that comparison where, since it's a fixed memory, almost all systems which are memory related, whether it's GPU, HBM, or whether it's DRAM, or even like disks, and even if you go back to floppy disks, it's like contiguous, accessing contiguous memory locations is always faster and more efficient than accessing like random points in the memory space. Um, so most of the infant system, they adopt this contiguous memory space framework. Um, but however, that doesn't work when you have like dynamically growing and shrinking inputs. So when it is fixed length, fixed, everything fixed, it works really well. But when you have dynamic growing and shrinking, it doesn't work well. Um, and they talk about like why it doesn't work well. So one is like this internal fragmentation stuff where you might allocate more than it actually needs per request. The second thing, they also interesting thing they mention is, say suppose I have two requests at a time, and one request is like very small. What is the capital of France? And the answer is just one word, and it's a very short context length. And the other request is like a very complex physics problem and has like a very long token length. Um, I could correctly reserve the memory space for that very long token length. Say suppose it was 3,000 tokens and I correctly reserved it, but I'm not going to reach the 2,000 token until like 3 milliseconds or 3 seconds later, based on how long it's going to take me to fill in all those tokens. In that much time, I could have easily used that memory for answering what is the capital of France and given. So even if you correctly allocate the space per request, you might not use that space, and someone else could use it in the meantime. So there is also like another form of internal fragmentation they talk about. Um, yeah, so they propose the solution to this is like, let's separate out physical memory from logical memory space. Basically, take the KV cache memory space divided into blocks or pages in traditional virtual memory stuff. So you divide it into block, and you decide each block contains how many tokens. So you can say like each block is defined by like 5 tokens. So you'll be always allocated 5 tokens in one go. And in your logical space, they are contiguous, but in your physical space, they're not contiguous. So you allocate on the fly. Yeah, Raja.
Yeah, I wanted to ask, you referenced like a tier of storage where you talked about disk, floppy disks, system memory, et cetera, and that it being more efficient to access sequentially rather than random. And I'm just wondering if you had any insights into the GPU memory, like like, so I know on a disk, right, that the kind of the layout, the sequential nature of the layout on a disk, but what are the physical constraints on a GPU memory? Like there's going to be
Um,
some length where it's, you know, sequential matters or sequential doesn't matter.
I'm not sure exactly if you are already on the GPU memory, how accessing it is different. But when you look at like copying, for example, CPU to GPU memory, you would have to do like multiple copies, and that would increase your cost and your PCI bandwidth usage, for example. So if you have
Okay.
like a pin sequential memory, you just do one copy of a large number of bytes, and that reduces your number of copies basically you do. Um,
Okay,
that
so kind of it's a transfer of a chunk of data rather
yeah,
than one
yeah.
word at a time type of thing.
Yes. Yeah.
Gotcha.
But I'm pretty sure there must be some semantics around accessing even after coming to GPU, like what access is faster. There might be some semantics around it because like even inside GPU have like these levels of caches and
Yeah.
yeah, so there might be some semantics
Well,
there.
and some the bus in and the GPU I think is quite wide. So access you don't if you access just one byte on there, it's going to be very efficient as opposed to some, I don't know, 200 bytes or something like that is one access, one memory access.
Yeah. Ted?
Hi, Neha. Thanks for covering this. I've been monitoring the chat, and I think maybe just to make sure everybody's on the same page around like internal and external fragmentation, um, it might be good to just kind of walk through a little bit about uh, how these things can happen. If you want, I can do like a couple quick examples, or yeah.
I can give a try, Ted. If I'm still not able to explain, maybe you can go ahead. There's this example in the paper on page 4. Um, so this is, let's look at just the request A part of it first. So the request A is basically your prompt, right? So it's like for 1, 2, 3, 7 kV cache states is your prompt. Then once you have the prompt, um, you are going to do regression for it and you're going to generate tokens. So this is the autoregressive part where you go farthest brought forth end of state. So this is, um, oh wait, is this the autoregressive part? Sorry, I got confused. Um,
Yeah, I think you're right.
Yeah.
Yeah,
Mhm.
yeah. This is where the auto regression part is going on, and you are currently here. So if you look at yourself in time, you've just generated the broad. The LLM has just generated the broad word, and now it's going to go in future and generate these two tokens. Um, Now, at the current point in time, say suppose you knew how many tokens you're going to generate. So you know you're going to generate two more tokens. So this two tokens, you do need that space. So that is called the reserved space in this diagram. Um, and sometimes, like not sometimes, almost always, you don't know how many tokens you're going to generate in the auto regression because you don't know when you'll read end of state. So when you allocated the memory for this particular request, you allocated total how many ever, whatever is the max context length that is applicable to that model. So you allocated up to this, like the space here. But then when you finish generating, you realized, okay, I just generated these many tokens. So this space is basically not used anymore. So you allocated it for this request, but you never used it. So this is where internal fragmentation, this is what they're calling internal fragmentation. And you can see it, they show a similar example here where they allocated like 1, 2, 3, 4, 5, 6, and 507. Okay, so somewhere around like 512 token space for it. But like your auto regression ended somewhere here. So now you had like 507 slots which were never used during that period, like that request period. So you're kind of wasting the space. So this is internal fragmentation. Now, external fragmentation. So when you think of internal, it is within a request allocated space. So you allocated the space, but you didn't use it. External fragmentation is basically saying you never allocated the space. Now, what happened? Say, suppose there was another. How do I explain this? Say suppose before this memory state, there was another request which was allocated from here, from this point onwards. And then that request got over, so you deallocated the memory, and then another request came in and you allocated it from here. Now you have these two token spaces left. Every request which comes in is going if it is longer, if it requires KV cache space which is longer than these two token space, it's never going to use these two token space. So there is memory there, but because you're using memory in such a fragmented way, with allocating, deallocating, you have space in between which is not big enough to be allocated to a particular request, and you have many set spaces in between, so that causes external fragmentation. Does that make sense?
Yeah, if I could add a little bit of color to that. So if you are running on your laptop and you're the only person and you're only doing one request at a time, okay? So then you ask it, what is the capital of France? And the model says the capital of France is Paris. And now you're done with your request. What you can do is you can zero out the entire KV cache and wait for the next request. And then you type in, why is the sky blue? And then why is the sky, it's 5, okay? So it has to allocate 5 tokens on the KV cache. And then as the model answers and it says, now you need the KV cache size 6. Sky, you need 7. Is blue, you need 9, because now you need a KV cache size 10. If you're the only user, you can just have this big chunk of KV cache and you just start at the beginning and you keep allocating tokens as the KV cache gets bigger. And the only problem you have to worry about is running out of GPU memory. But exactly what Neha was saying is now let's say you've got multiple users and you've got a batch of 3, and the first one is something long and the middle one is what is the capital of France? And it responds the capital of France is Paris, and that's, I don't know, like 12 tokens or something like that. So even if you and then you have this third request that's also long. So you have this dilemma that if you don't know how long each request is going to be, one safe thing you can do is just allocate the maximum possible length for each one, and you'll never worry about running out of memory. But then you'll have the dark brown and the dark green, tons of internal fragmentation. And now that we have these models that can do maximum context length, 100,000 million, you're really going to allocate 1 million tokens just for what is the capital of France? So that's the far left column, is if you just max everything out, you get tons of all this empty space inside each request that you've allocated max length. Okay. And then even in the third column, if you had a perfect oracle, okay, and you knew that the second request was what's the capital of France, and it was only going to be a KV cache of size 12 ever needed, and at the beginning of that request, you allocated 12. Great. Things look really good right now. You've got your first request, the second request has finished, the third request is still going, but now you have this hole. Once you complete the second request, you have this hole of 12 tokens between the first one and the third one. That's like the little gray area that Neha showed on page 4. And, all these types of situations are just going to keep getting worse and worse. The longer you're running and the more requests you're serving, you're going to get all these little things where you have some requests that took up some space and it's not enough for the next one. And so you're going to have memory in between KV cache chunks. And there's different algorithms you could do that kind of mitigate the problem. But what they show is that the other stuff that people are doing, none of it works really great. And so then, like Neha said, so then you can take a page from virtual memory, and then you always allocate KV cache in, say, chunks of 16 tokens. And then you'll never have external fragmentation because everything is always going to be in equal size chunks. You still have a little bit of internal fragmentation, but it's only up to 15. It's not so bad. So there was a little bit of discussion in the chat. I hope that that level sets as to like the problem we're trying to solve. Because again, if you were the only user on your laptop doing batch size equals 1, we wouldn't need VLLM. Life would be so easy.
So Ted, is that more like a demand paging sort of scheme?
It does end up being that, but the idea is that yes, in fact, it is exact. Well, I don't want to steal Neha's thunder. It is going to be exactly that. When you use up the 16,
we can come back to that, but
if we give you 16 and you decide you need a 17, then you're going to have to get another 16. It's exactly like that.
Yeah. Okay, I got it. I think Neha, please continue.
Yeah, I can't read the chat somehow. So yeah, if you guys can just interrupt if you want to talk, like that would be great. Yeah, I can't see the chat. I can see hands up, but I can't see the chat. Yeah. Yeah, so this is just an introduction about how transformers, how they work, the prompt phase, that is the pre-fill phase. It's like compute heavy, something we went over before, and the autoregressive or the decode phase, which is memory bound.
Neha, just do you have the chat thing on the bottom of your screen? It says like 10 now, mine does.
No, I don't. I think
Oh,
when I started sharing, it went away.
okay.
Yeah.
Okay. Well, that's a bummer. Okay.
Yeah.
I can relay something if we had any questions or whatever, or if we're.
Yeah.
Yeah.
Okay. So yeah, I think we went over some of the memory challenges in LLM serving, but this was a really great example on how big actually the KV cache is. So if you have like a 13 billion parameter OPT model, I'm not sure which model this is, but I'm assuming some LLM. The KV cache size of a single token, calculated like this, comes out to be 800 kilobytes. So if you have 2048 token, it almost can be as big as 1.6 gigabytes for one request.
I think that's an important number to keep in mind because it's not really obvious that each token gets expanded that much into the KV cache. It's huge.
Yeah. Yeah, it's like you multiply by the number of layers and like the hidden state size, and it just blows up. Yeah.
Yeah, if you think of the representation capacity of that, to me it seems huge. It actually seems larger than it needs to be, but it's a big number.
Yeah. Yeah. So
Yeah,
this.
in fact, as we get these really large models with long contexts, they split up the model across multiple GPUs, and it gets to the point where KV cache is 90% of your GPU memory, not the model, which is never the way it used to be, just like you said, Neha.
Yeah. Yeah, so this was like eye-opening for me. Like I always knew KV cache was big, but when you look at the number, it hits hard. Like even like on an A100 or 40 gigabytes, you probably can't serve more than like how many, 20, 30 requests per GPU. It kind of gives an idea on how much OpenAI is spending on GPU. But anyways, yeah, so so basically the memory challenges is definitely this one large KV cache. The other challenge they also talk about is there are decoding algorithms like beam search, which don't just decode once, but can take like n different paths and choose like the best path for decoding. So those would also increase like some of the KV cache, like the amount of KV cache needed, as well as they would require advanced cache sharing techniques. We go through an example of this in the at the bottom of the paper. So if you don't understand, that's fine. So those were like two big problems, and then the third one we've discussed multiple times right now is like the input and output length is variable. So those are like the three big problems. Then they talk about the same problem which just Ted explained, where like traditional systems, they usually just fix the amount of memory per request, so you have a lot of internal fragmentation. And even if you knew what is the length of tokens you need, even then you would have external fragmentation, and you would for long context requests, you will be holding that memory for quite a while, so someone else won't be using it. So let's go down to the paged attention example. Okay, yeah. So this is basically the paged attention, the way you map like the physical space and the logical space to each other. So in this request, your prompt is so and so, and then your output or like the decoding phase will generate father's broad. So in the prompt phase, you would basically you're the block size. So by block size, they mean the number of tokens per page. You can think of that. So like the block size is like 4. So you'll always be allocated space for 4 tokens at a time. You can't be allocated like 2, 1, or 3. You'll always be multiples of 4. So this one, the prompt is 4 score and 7 years ago. So this is 4 scores and 7 years ago. You have a block table, which basically says like this logical block 0 maps to this physical block 7, and the number filled is 4. So all the 4 tokens are filled. And then years ago are blocks maps to block 1, and 3 tokens are filled, 1 is not filled. And then when it starts decoding, it decodes further, and it realizes it has one space in this block. So it updates the number of fill to 4, and it places fathers there. Then the next decoding, it says, okay, I came across brought, but there's not enough space in this physical block 1 because it's already a token length 4. So I need to allocate a new block. So it goes and allocates block 3 and places 1 token here. So it will basically continue that process until end of sentence, and it will stop allocating the space. So in this way, the only, like, say suppose R and E and our statement came after this, you would be only wasting, you'll have internal fragmentation up to just 3 blocks here, 3 tokens here for each request, compared to like 500 or 2000 tokens in the above example, which we saw. So at the max, you will have like 3 token space wasted per block. There's one really important thing here. You need to choose your block size correctly. If you choose a too large block size, then you increase your internal fragmentation, and you also you also can't share. Okay, let me talk about that when we go down, but you can also share these KV cache with other requests. So you reduce the amount of sharing between the KV cache between the requests. But if you take a too small block size, they don't really talk. I wasn't able to read it till the end of the appendix and everything, but I wasn't sure if we choose a too small block size, would it affect performance in a way that you are you're jumping around the memory too much. So that part wasn't clear to me. But yeah, basically, Jerry, this answers your question.
Hmm.
Yeah, it's basically the same way.
Okay, thank you.
Yeah, I think one of the bigger issues is if you have a very small page size, block size, then you're increasing the overhead of managing the blocks,
Yeah.
right? So there's only two. I mean, here four we're showing just so it fits on the diagram, but they don't actually use four. They use a bigger number. And so you can imagine that if it was two or four, you're constantly asking for new blocks. And so it's probably
We're
not huge, but it is extra overhead in terms of memory and compute, memory for your block table and
right.
compute for allocating all this stuff.
But worse, if everything is full, you've got to you've got to shift things out somewhere, then free them up, and then use them, and then you get into kind of this thrashing type scenario.
That's true. If you need to do cache evictions, then the smaller the blocks are, the more evictions you're doing more frequently. Yeah.
Right. And the more cycles you're consuming doing that versus real work.
But at most, you're going to need batch size number of partially filled, empty or partially filled blocks. So it's not a huge amount of memory.
Yeah, but while you are at it,
I was-
why not just, clean up, just do the garbage collection, because then you will have to do it again for the next request.
Yeah.
Yeah, and I mean we'll get to it. They do that, but in general, having small blocks introduces more overhead. I think that's what we were talking about.
Right.
Neha, I was wondering, do they talk about, are the blocks defined as a per layer structure or per token position?
They defined it per token. So the block size is equivalent to a fixed number of tokens. So they would choose they would save all the KV cache values for a particular tokens together, given that so let me go back to this example. Like if you shard the model n-1 ways, n ways, then for this particular shard, for the KV cache on this GPU, it would store all the KV cache values for a token together, and it would call it like one token and then n tokens from a block.
Gotcha, thanks.
Yeah, so if I can add to that, like if you shard model by layers, then you can split the KV cache by layers.
Yes.
But if you shard it any other way, then you basically keep the KV cache all there. So in the simple case where the whole model fits on one GPU, then there's no need to think about it in terms of layers. But I'm pretty sure the current modern version of the LLM, it does support having different layers on different GPUs, and then it'll only keep the necessary KV cache on there. Neha, you've got two more raised hands. So
Yep.
Terry and then Dave.
Yeah. Terry?
I have a question. I think in general, the memory access is faster when the memory layout is continuous. So does that mean, or is that correct? Or does that mean this kind of page attention will have worse performance than the continuous layout?
If you can fit the number of requests in a single machine very well without like if your intention is not to increase throughput, then you probably wouldn't go down this route and just like have contiguous memory location. But given the context length which the current state-of-the-art LLM support, you would probably be just doing one request per GPU, which wouldn't be scalable. Yeah, so you would prefer to go this route, even if it comes at the cost of a little bit of efficiency. Little bit of latency. But they also down below, they also talk about like the CUDA kernels they've created for optimizing all these memory management and all these operations. So I'm assuming that the latency impact is not a lot because they also share in the abstract somewhere that they were able to get neutral latency to to this Orca framework. So I'm guessing, yeah, it might not impact latency that much, but logically or maybe semantically, it feels like it should affect latency, but they might be doing something else too. Yeah.
Okay,
Yeah,
okay.
Yeah,
like
so
I haven't read the paper. Yeah, yeah. Thank you, thank you.
yeah, so Neha, you talked about how big the KV cache is. So if you have a 20K um, uh, token entry and your page size is 16, that means that one little block of 16 tokens is 320 kilobytes, which is
Yeah.
a pretty decent size to be fetching from HBM in one
Right,
request.
right. Yeah, that is also true. Yeah, yeah, yeah. That makes sense. Yeah.
Thank you.
Dave, you had your hand up.
Yeah, my question was similar around the page size and the alignment with the virtual memory on CPU page size versus the size of each of the cache blocks. Is there any study correlation around that as well?
Let me. Yeah, I'm not sure about that. They do have like a few graphs in the end where they study the different block sizes here, end-to-end latency with different block sizes. So as you increase the block size, kind of the latency increases. But this might be
Yeah, it's okay. I mean, we
yeah,
can come
yeah,
to
I
it when you come to
haven't.
that. Yeah.
Yeah, I haven't actually, I didn't reach till there. So we'll see. Yeah, so that was, yeah, this is a similar example with two requests happening together. Basically, the other request will pick up a block, a physical block, and then as it goes and decodes, like it reaches best, it realizes it needs one more block, and it will pick up more block from the physical KV cache. Yeah, so now this is where they go one step further and they say, okay, not only are we going to use the memory efficiently, no, not only are we going to use the memory completely, so I have no wasted memory, but we are also going to see if we can share the memory. And one of the two common examples of sharing, or three common examples of sharing memory is one is like parallel sampling. So, for example, you just have a single prompt, but you want to generate two different responses for it. So, in this scenario, they introduce something which is a copy on write semantic. So let's just go to the example. Basically, it says four score. So this is your prompt up to R. So initially, it will just have two blocks for the prompt. So the block 7 and block 1 will be allocated for the prompt. You want to generate two samples, but the prompt for the two samples is the same. So you just allocate this one. But in the end, you're going to have two results. So you add a reference count to this, and you say a reference count of 2 because you're going to have two sequences being produced out of it. Now, when the decoding, the autoregressive phase gets scheduled, basically you come to fathers, and then you immediately come here and you say, okay, I have one spot and I can write it here. But you realize the reference count is 2. That means two people are referring to this block. So it is not safe to modify it in place. So you copy it. So you copy it only when you start decoding it and you realize you need a copy. And then you take this pointer and point it here basically. So now this one points to block 3. and you reduce the counter by 1. So when this one comes and says mother, it comes here and it has an open token position and the reference is 1, so it uses that space. So in that scenario, you didn't have to replicate block 7. The block 7 is shared between the two requests. And this is particularly useful if you have like very large prompts which need to be shared. So this is one way they enable KV cache sharing. You can use these same semantics for beam search. So in beam search, what you would basically do is you would start with a single prompt. And then while decoding, instead of decoding one, you decode multiple. So in this scenario, for example, instead of decoding one at one point, you're decoding two of them. So the moment you decode two of them, your block 0, this is block 0, is common across the two candidates. But you have block 1 and 2 separate. So this is block 1 and this is block 2, for example. And then you keep decoding and you keep generating blocks. And at some point in the beam search example, you will start canceling. You will start losing the candidates and only choose the promising candidate. So in that scenario, if you come, for example, you come at this point in beam search, you realize that block 0, 1, 3 are shared for all these three candidates, 0, 1, 2, and only 5, 6, 7 are different. In a traditional, if you didn't have pageable memory and you didn't have like memory sharing designed this way, you would basically have to you would have 3 blocks here for this candidate and 3 blocks here for this candidate as well. So you use less memory for applications like beam search because of like KV cache sharing. And then the same is applicable, I believe a lot of use cases nowadays do like batch inference to generate their own fine-tuning data, or like generate their own training data for downstream models. In that scenario, you usually have the same prompt like this, like translate English to French and with some examples. And then, but the task input is different and then the output is different. So in this case, you don't need to really create a new KV cache for the prompt, the shared prompt or the shared prefix all the time. So that can also be shared using this mechanism. Yeah. Yep. And then this is where they talk about eviction. So what happens if the KV cache is too big? KV cache goes out of memory. You have two options here. One is you lose the cache, you choose and you move the cache to, you choose certain blocks and you move them to CPU. And when you have space, you bring them back to the GPU. One of the things which they do differently is basically they don't move individual blocks to CPU. They move blocks for an entire sequence or an entire request to CPU. So they don't evict per block, they evict per sequence. And especially in this beam search example, they evict the entire beam search to CPU. So you kind of always have all the blocks associated with you kind of only impact one request. So you don't like randomly choose blocks and give them out, and 2, 3 requests are waiting for that block to be available. It usually just impact 1 or 2 complete requests. That was one. The second is they also, once you reach like a full GPU KV cache, you would pause receiving more requests so that you don't create like more burden on the memory. You're not like you don't reach that stage where you're thrashing stuff out and like you're not in a stable state with the GPU memory. So you kind of pause taking in more requests. Yeah, the part which I didn't understand was how do they choose which request to evict or which sequence to evict? Um, so they do mention like they will evict an entire sequence, but it wasn't clear which sequence to evict. The other part also, which was part of the other option, instead of like offloading it to CPU, the other option they say is also like recomputing the entire KV cache again. And it is not as expensive to recompute because, say, suppose your pre-fill had like 10 tokens and your decode had like 20 tokens, but you'd only finish doing 10 of them. You won't be doing decode for 10 of those 10 again. You would basically take 20 plus 10, 30, and you would do a pre-fill and then do the last remaining 10 decode. So they say the latency is not as high as the original latency when you do recomputation. But yeah, that is also an option. Like you can just delete that one request and recompute it later. There was one. Yeah, this was the
And
part.
Neha, I think Roger has a question.
Oh, sorry, Raja. Yeah.
Yeah, so my question rolled back to actually the parallel sequencing examples that you had.
Mm-hmm.
Yeah, the beam search and parallel sampling. So we've talked about this type of workflow before, and then kind of the architecture supports it. The question I had is in your real life work experience or exposure to other real life applications, are people using VLLM, these capabilities of VLLM, kind of more parallel decoding sequences or sequences?
I have seen it for a very specific use case for optical character recognition because um, that is where you require accuracy. So you basically, especially on like content which is generated by like manually written, handwritten stuff, it is very hard to figure out if like I start with an A, is this going to turn into a valid word versus I start with an E, is it going to turn into a valid word in the end? So you would maybe try to predict like 3 characters or 4 characters, and then you're like, okay, this looks more like a word, so I will go with this. So I've seen it in those examples, but I'm not sure about like um, chat GPT style applications if they really do it. Yeah.
Oh, okay, that's very helpful actually. So it not necessarily because we've talked about it usually in the context of parallel sampling for text generation. Um, but what you're saying is there's certain use cases where that idea that you're evaluating multiple potential interpretations and the kind of the more probable solution comes out later in the process. Um, yeah, that's very helpful. Thank you.
Yep. Yeah, so this is the part till where I read. So the remaining part we're just going to figure out as we go. The kernel, so these are the kernels they basically developed to implement some of these memory access patterns with like page retention, basically. Um, Fused, reshape and block write. The new KV cache has split into blocks, reshaped to a memory layout optimized for block read and saved at position specified. We fuse them into a single kernel. So is this where they write and read together, the new? I think so. No.
I'm not familiar with this one specifically, but it does seem like a lot of the fragmentation issues that you described earlier are related to the fact that implementing a matrix multiply assumed that both matrices
Right.
are contiguous. And so in order for this type of algorithm to work, you're going to have to understand that the memory is not contiguous. It exists in different chunks. So I was wondering if they had to have some lower level CUDA kernel implementations that would be optimized for
Right.
non-contiguous tensors.
Right. Yeah, I
Yeah,
thought.
and
Go ahead.
I
Sorry.
wouldn't dream of like tomorrow trying to write this code. But if you know that the matrix multiply is being done on 16 by 16 tiles anyway, then having your KV cache in chunks of 16 isn't really going to change the matrix multiply algorithm very much.
Yeah.
Does that make sense, Roger?
Um, I'm not sure. That my understanding of why we were getting the fragmentation, both internal and external fragmentation that Neha was describing early on, was I understood it to be this requirement that uh, these tensors are considered contiguous in memory. They weren't broken into a bunch of different pieces. So when you're talking a 16 by 16, are you thinking in terms of um, like some sort of image tile or something like that?
No. The fragmentation comes from the fact that you are growing KV caches for each request as you decode one token at a time for an unpredictable amount of time. So just imagine in the old C days, if you just are calling alloc one item at a time as you grow a list or grow a tree, and you just have no idea when the user is going to stop, you can just get terribly fragmented memory if
I
you're
thought
doing
that
this.
I thought there was actually the internal fragmentation was because they pre-allocated for the maximum sequence.
Yes, so larger allocation chunks reduces the number of times you need to allocate, but it creates internal fragmentation. Okay. And so in the extreme, you could just allocate max sequence length all at, at up front as soon as you get a request, but it's going to have terrible internal fragmentation. You're going to get external fragmentation no matter what you do if you have unequal sized alloc commands.
Right.
So that's where paging solves both of those problems. It reduces internal and by having fixed size, you never get external fragmentation. Every chunk you free up is always on a multiple of 16 boundary if you're using block size 16. So
Right,
separate from that,
but it needs to understand that if I'm multiplying um, something that's a sequence of 34, that's not actually 34 consecutive. That's 16 and 16 and 2. They're
right,
one matrix conceptually, they're actually different memory blocks.
right. So what I'm saying is that if you actually had contiguous 34 by 34 matrices that you were multiplying, likely what NVIDIA is doing at the lower level is it's breaking them up into 16 by 16 tiles. And they're doing a few 16 by 16 multiplies. 34 would be 16, 16, 2.
I,
So a few 2 by 16 and 16 tiles.
okay,
And
I
occasionally in that corner, a 2 by 2, which is kind of inefficient.
Okay, I understand what you're saying now. That inside the CUDA kernel, it was probably broken down into even smaller
Right,
units that optimized for the GPU. Yeah.
right. So if you are multiplying Q on the left times K on the right, you would like your Q to be physically row order, or I don't know what the right term is. contiguous memory, and you'd like your keys to be column-wise contiguous in memory. And so basically, if you have an intelligent KV cache that's trying to support this column-wise business, then you always store your queries row-wise, you always store your keys column-wise, and then they're going to get served up by this custom kernel in these 16 by 16 chunks anyway, except for the boundaries where it's not a multiple of 16.
Yeah, so the kind of the external interface to the kernel changes because now it's not 34 tokens, it's 16 and 16 and 2. But inside of it, it's still going to be broken down into these GPU optimized, these hardware optimized sizes.
Yeah, so I think that part of it doesn't really change as much.
Yeah.
What does change is you have to do this one extra step. You have to go into the page table to figure out where the logical page turns into physical page. And so I think that's where you get extreme amount of benefit by lumping the logical lookup and the physical page retrieval in one call instead of having it be multiple calls.
Yeah. Bobby?
You got Bobby there. He's got his hand up.
So what does this block contains? Does it have the embeddings or the Q or KV for the KV cache?
It will have the KV for the KV cache.
Oh, okay. Each block contains the key and the values.
Yeah.
Okay, thank you.
And I think we said it contains the K and V for all the layers for that token position.
Yeah,
Right.
located on that machine.
Right. And after you've multiply it by the W sub K, I don't know what to call it, embedding matrix for keys. So it's not the raw input token, it's the token after turned into a key vector. And so those, every time you get a new token, you dot it with the query in order to calculate your attention weights. And you can recompute those, but it's much more efficient to use a cache than to just recompute them.
Bobby?
Oh, sorry, it was from the early time. Yeah, sorry.
Dave?
Yeah, sorry. I have a question related to what I think Roger was asking, and don't know if it was somehow I didn't hear the full conversation. But anyhow, so it was about the capabilities of the tensors, sizes for multiplication versus how to determine the block size. Is that how it was that you were talking about, Roger? In like tensor multiplications, specifications, and then how to correlate that to the
Yeah,
So
so just
typically,
restating, it was basically that if you have a naive CUDA kernel interface that's going to multiply two tensors and they're very long, that it assumes each of those tensors are contiguous.
Yeah.
That's part of what drove some of the early fragmentation. That's what my comment was.
yeah. Also, people who implement these like SGLang, VLLM, or Llama CPP, and all these inference engines or TensorRT, they essentially build for the target architecture. They will have a different mechanism in the inference engine so that it's optimized for the target architecture, and it will automatically identify which architecture you're running on and take you in that direction. Now, at a higher level, they will come up with the recommendations, which they will probably publish, that if you're using Quen, this model, they know this is the number of layers, this is the per kilobytes per token or megabytes per token, and so those that way, that probably will be some multiple of the I guess target architecture, or maybe they will do some auto mapping so that it is optimized for that. But then if you up level it all the way to the CPU and OS and the uh, page size and other things, that I think can also change depending on when you install the OS on the system. You can decide your page sizes, right, depending on the target applications and all. But at least between the KV cache for the model to the inference engine, uh, I think the inference engines definitely try to optimize and provide the best practices and guidelines for that.
Yeah.
Dave, is that the language model frameworks that are doing that type of optimization, or is that more down at like the CUDA kernel that they're doing that?
So not everyone is writing the CUDA kernels directly these days. So there is this intermediate language called Triton, which has taken off big time. So it's kind of in between Python and C++ of CUDA. So you write in that, and then the Triton compiler will map it to the appropriate CUDA, or like translate it to machine language, whether to CUDA, and then machine language that I don't remember. But these days, everyone is writing in Triton. Like the fast attention, for example, right? From
Right,
Stanford, that was written in Triton. That he was one of the first users who made it, made a super useful application out of it.
right. But I
Yeah.
guess
So
the question I was wondering is that the language platforms, the inference platforms that are doing that optimization, um, or,
well,
or is it the
it,
guys that are writing the Triton kernels?
so uh, so I think in this case, I'm trying to think. So there, if people are writing the kernels, they will write the kernels for the LLMs as well. So yeah, that's a good question.
Yeah, no, I can see where different models have different
Yeah.
optimizations. I mean, look
So
at DeepSeek, right? They did a lot, I think, a lot of kernels that development that they did. I
So
don't
they
recall.
worked, yeah, and then they did a lot of that, and then came along SG Lang, and then they said that, look, we are the first ones to deploy DeepSeek, and we run fastest of all other inference engines. So it may be a combination of some sort. I am not. I mean, what DeepSeek did was all the way low-level optimizations for communication and including what you mentioned, right? The uh, computation and everything. When it comes to KV cache related optimizations, like how to allocate the block sizes and any other thing, I think that is the alignment that they need to do with the kernels. And if there is any kernel fusing that they can do, which Neha talked about as well, right? Kernel fusing, then maybe they also do some of it.
yeah, I think it's a combination. Like if the kernel is like open source and they can use it and it fits easily within their inference framework, they won't be rewriting the kernel. Like most of these open source teams, they want to catch up with state of the art fast. So they might reuse how much ever they can, but if it's not available, they they'll write their own kernels basically. So they have like research happening on the other side as well, where they're trying to figure out the best ways to do certain operations. Yeah. Okay, so we are at the evaluation. So these are basically the different Orca implementations they have. So this is like they implemented their own version of Orca. The tree ones, the Oracle one, there's no internal fragmentation, only external fragmentation to allocate as much, and then the max is where they allocate the maximum token length supported by the model. So in all of these, you can see that the latency kind of remains the same. They're not optimizing for latency, at least in this paper right now. They might be, that's a different thing. But when this paper released, the paper is not optimizing for latency, but they're trying to serve more requests per second in the same latency. So it kind of, and they tested across like different model sizes, and different number of GPUs as well, is it? Yeah, and two different models, this Alpaca model and the shared GPT model. Yeah. This is
Neha, I'm struggling a little bit with what that graph is saying. What are the data points on there, and why do they go off the top of the chart?
so as they increase, so let's look at one example, the green one here. The green one is for Orca Oracle. So as you increase the number of requests per second, you're going to basically utilize more and more memory. So the requests would have to wait to get enough memory because the memory management is not efficient in Orca Oracle. It has a lot of external fragmentation. So it would have to wait for sufficient memory to be available for it to schedule itself, so the latency would increase. So
So
as
are the markers like the nth token? Is that what that is?
yeah, it's nth request rate per second. So I believe this must be like 3 requests per second or something like that. This is 5. This is 7.
Oh, okay.
Yeah, this looks like
Okay,
7.
I was trying to relate the markers on one line to the markers on another line, but that's doesn't make sense then. It's for each model, when it's running at a certain rate, what does the latency look like?
Yeah, yeah,
And you just have some random samples that you
yeah,
plug in there. Okay.
yeah.
Thank
Yeah. So yeah, they basically, and then this they do it with beam search and um we should compare these two because beam search should have a higher latency. Oh no, sorry, beam search is this one. Yeah, I'm not sure if we can compare this graph with like the graph here for beam search and parallel search, where I think the trend is obvious. You can obviously serve more throughput at the same latency. Yeah, this was the one which I was really interested in, was like and how the latency differs with different block sizes. Um, so as the block size increases at certain block size, they get an optimal latency at like 16 or 32 block size, and then it starts increasing again. Whether this was the charge, if the block size is too small, VLLM may not fully utilize the GPU's parallelism for reading and processing the KV cache. If the block size is too large, internal fragmentation increases. So the probability of sharing decreases. From 16 to 128 lead to the best performance, while 16 and 32 work well. Yeah, so larger if your block size sequence becomes shorter than the block sizes. I didn't get this part.
So the key thing to understand is that we're measuring things with one level of indirection. So when we have inefficient memory utilization, what happens is the number of user requests that can be handled at once goes down, and the number of people who are waiting to be processed by VLM goes up.
Right.
That's why the average time seconds per token goes up. It's not going up because it takes longer for the LLM to process any one given user per se. It's going up because there are more users waiting even to have anything happen, and there are fewer users that are actually being worked at any given time.
Got it. So, but then why do they say like larger block sizes significantly degrade the performance since the sequence becomes shorter than the block size? Is it because this causes memory inefficiency and has hence the consequence, or is it?
Right.
Okay.
Yeah, it's a two-step process. The internal fragmentation wastes KV memory, causing the server to be handling fewer users at once.
Right. Right.
So maybe with a small block size, it can handle 10 users at once, but with a big block size, it can only handle 8 users at once. That means that on average, people are waiting to even get started being served longer. But once they do get served, they'll probably get very similar times, if that
Right.
makes sense.
Right. Yeah. So the time to first token might be higher, but signal, the next tokens might be the
Yeah,
same.
and we could get into the really gory details, but high level, I think that's the intuition is that time to first token goes up and the other times will be relatively. Yeah.
Right. Yeah. Um, yeah, this one was the other one, like when they recompute versus swap. Um, so for very small block sizes, the swapping actually has a higher latency, whereas like at some point they are equal, and then the recomputation has a higher latency. Yeah, I'm guessing when the block size is larger, you are recomputing for more tokens, and that's why it is more difficult to recompute. Nah, I don't know. It doesn't make sense. Um,
We have a hand raised, so yeah, go ahead, Srini.
Oh, yeah, if you look at figure 18, one page before, you can actually see the effect of latency on the figure 18A. The VLLM introduces the costs associated with indirect referencing of pages.
right.
So that's latency has increased, I guess. That's how I don't know if I should read it that way. Compared to, I don't know what they are comparing it with.
I think this is fast transformer or something. There was one more,
Okay, so it's not the traditional system versus
yeah,
the.
this faster transformer. It's some traditional
Oh,
inference.
okay. So it did. They do show that there is an increased cost in terms of latency, but it's not high. I guess the difference between the FT and VLLM is not that huge, but it is higher.
Right. This is in microseconds, so it's like a few hundred microseconds higher. Um,
Okay,
yeah.
thank you.
This is just the kernel latency, right? So it will account for the paging, finding the physical page.
So
Yeah.
how do they measure this latency? Is it measured in the GPU or is it measured all the way to the response from the CPU?
I'm not sure.
Since
Yeah,
it
The
is
kernel latency
microseconds,
would have to be at the GPU.
yeah,
right? That's what I think. It's because they are reporting it in microseconds. So I would think they have some tools that measure it at the GPU level.
Yeah, NVIDIA
Yeah.
has profilers that can do that.
yeah. You can use Insight profile tooling.
Right, right.
Bobby?
So in this diagram, 18A, so it looks like the lower context length will actually has a lower latency, but if you increase the context length, it is increasing. So, and also with the batch size as well, it is diverging pretty heavily because of the memory pressure, right? So within all the KV cache, I assume.
Yeah, like increasing with context length is probably expected. Um, because you would be like if so when we say kernel latency, it's like I'm assuming is it the LLM kernels latency or is it I'm guessing it is these fused kernels and the extra work they do. and compare it with its equivalent kernel on the faster transformer and comparing those. So that would make sense because as your sequence length increases, you need to figure out more blocks and stuff like that. So you would need more latency. It would add to latency. Yeah,
I'm,
my
I'm
hypothesis.
assuming it is due to the memory pressure. So if you
Yeah,
increase the contact length, then it is going to be you need to keep track of more tokens in the
right,
memory.
right.
And if you're having a larger batch size, that means you're handling more requests at the same time. So it adds it multiplies the amount of memory required. So that's why the graph is trending upwards
Right.
when those two values are increasing. Yeah.
Yeah, makes sense. I just wanted to pause here for time check. It's like 8:05.
Yeah, we probably should look at finishing up here in the not too distant future.
I think the only thing is left is this graph. Everything else is just related work and conclusion and stuff. Yeah.
On that graph, what I didn't quite have an intuition of why you're looking at normalized latency. Why is the small block size higher latency? And then it drops down. I can get why it's
This is for recomputing and swap. I'm guessing this is when your memory is already full and they're comparing the two strategies, whether you should offload to CPU and get it back versus discarding it and then recomputing it from scratch.
right. So I understand that. Yeah, the purpose of this graph is comparing the two. Both have a similar upturn in the normalized latency for small block size. And I think that was also reflected in the earlier ones that we were looking at there. I thought I saw, yeah, see how it's higher for small block size and then
Right.
down.
Yeah.
I didn't have an intuition as to why the small ones would be higher.
The small ones.
On figure 18 or on figure 19?
Well, both of them have that kind of downward uh, curve in the beginning between 1 and 16, I think. Although maybe they're different units. Sorry, this is block size, but the other one was
I'd have to
sequence
double
length.
check the tests. I don't think figure 18 necessarily um, involves a lot of cache overflows. But figure 19, I think, is expressly designed. Let me
Okay.
double check.
But if you look at 18, it still has that dip, doesn't it, in the beginning?
Yeah, because small blocks are really inefficient. There's tons of overhead.
Okay. Okay. It's all the indirection. Okay.
Right, just
It's because in figure 18, the left picture, there was a divergence between the FT and the VLLM. Whatever
right,
it's
exactly.
yeah, okay. Gotcha.
Yeah,
Yeah.
go ahead, sorry. Uh-huh.
I didn't understand the overhead. So, for example, if the overhead is going to be fixed, whether you're doing it for the smaller block size or if bigger block size, right? If the bigger block size is not actually adding more complexity, then it should be like yeah, if the overhead is X and if the overhead is for the bigger block size is going to be Y, then Y is going to be much smaller than X. So it is going to be X plus Y is very close to X. So, but here in this case, it is like in the first diagram, number A. So, like the time milliseconds is 140 for block size of 1, and 256, it's all the way dropping to 20. Like it is almost 7x drop. It doesn't make too much sense.
So I think the thing to remember is they're not talking about memory load latency. This is calculate attention latency. And so this involves not just a load of a token, but rather loading multiple tokens and doing the matrix multiply against the query. And so this is what I think Roger was asking about. So if you can if you can do a very highly optimized matrix multiply and sneak in that little page lookup in the middle, you can hide most of the extra overhead. But for really tiny blocks, 1 or 2 sized page, you just can't hide that overhead.
Yeah, but
Also
if you look,
remember
if you,
that when the context is really long, we're doing massive matrix multiplies across multiple cores. And so we want those floating point cores to be highly utilized. And this is where I think the default is 16 by 16 tiles.
yeah, I understand. You're saying that the gain is coming from the parallelization, but here in this case, like yeah, even for swap in and swap out, so they are pretty high for smaller block sizes. If it is going to be just memory transfer, they have to be quicker when compared to the bigger block sizes, right? So
But when you swap in and swap out, you are swapping in um, you're swapping in the entire sequence here. You're not just swapping in one block. So you're swapping in same amount of data across with, and for lower block size, it means you're swapping more chunks of data, more smaller, tiny chunks of data. And for larger block size, you are swapping fewer big chunks of data. They don't swap in a block. They swap in the entire request or swap, like they do request level eviction.
okay, thank you.
Yeah. Cool. We'll pause here.
This was great.
Jared, you want to stop
Yeah.
the recording?
Yeah, hang on just a sec here.